In this video, we will go through we'll start chapter 2 and complete the topics 2.3, 2.1 to 2.4. 2.1 to 2.3 is about vectors and 2.3 and 4 is about 2D coplanar forces and addition of 2D forces. So we will work on the theory portion of this topics in this video, and the next video will be problem solving based on the theory. Chapter 2. Multiple forces in 2 dimension and 3 dimension. In this slide, we can see that a tower is being supported by multiple cables, and each cable supports some force such as F1, F2, F3, and so on. How can we find this resultant force acting at the joint on the tower? So for that, we need to add each one of these forces to find the resultant force. But remember that the force is a vector. That means it has both magnitude and direction. So we need to write each force as a vector quantity and add 3 vectors to find the resultant force. Same example, there is force F1 in this cable, there is force F2 in this cable, and we need to find the resultant force here. We can write that as a vector addition of these 2 forces. Now for vector, we will use this notation F and we put an arrow on top of that. That means it's vector. When we write anything without an arrow, that means it's scalar. So this is scalar, this is vector. There are a few more examples as shown in the figure. To find the resultant force acting at the hook while the car is being pulled, we need to represent each F1 and F2 as a resultant force and add them together to find the resultant force. Same here, we can add FA and FB to find the resultant force acting at the hook or for that crane hook. So objective is to resolve a vector for this chapter is to resolve the vector into its components and add 2 vectors using Cartesian vector notation. Which of the following is a scalar quantity? And the correct answer is mass. Force, position, and velocity, they all are vector quantities. And vector has both magnitude and direction. For vector addition, you have to use, and the correct answer is the law of parallelogram. There are 3 concurrent forces acting on the hook due to the chains. We will need to decide if the hook will fail or bend or break. To do this, we need to find out the resultant force of all 3 forces. And we can do that by representing each force as a vector and using law of parallelogram to add vectors and find the resultant force. And the practical application is that resultant force is applied at the hook. So we can make sure that the hook is strong enough to withstand this force, resultant force Fr. So some examples of scalar and vector quantity. So mass and volume are scalar. Force and velocity are vectors. Means you need both magnitude and direction to define them. For example, the GPS measures the velocity of the car. So it gives us the speed at which it's going, but at the same time it also gives the information about the direction, whether the car is going in the north direction or it is going in the southeast direction. So scalar has magnitude, vector has both magnitude and direction. Scalar can be positive or negative. Similar to that, vector magnitude can be vector magnitude is always positive, but yeah, its direction can be positive or negative. We can add scalar quantities by simple math. So if we have mass m1 which is 3 kilogram and mass m2 which is 5 kilograms, and together if you connect them to the hook, the total mass will be simply m1 plus m2. That is 5 plus 3 which is 8 kilogram. However, if it is vector, we cannot add it straightforward, but we need to find the resultant vector addition. Throughout this notation, whenever anything is in bold and red, that means it's vector. Anything that's not bold and red, that means it's scalar. Vector can be represented graphically by drawing arrow. So the direction of the arrow defines the direction of the vector, and the length of the arrow defines the magnitude. For example, this arrow and this arrow, they both are in the same direction, but this is twice the long as the first one, so its magnitude is 2a. This and this, they both have the same magnitude but opposite direction. This is going up, this is going down. This and this, they are in the same direction, but this is half of the length of the first one, so its magnitude is minus 0.5a related to the first vector. Now to add two vectors, we can use law of parallelogram. So in law of parallelogram, there are two different ways. One is law of parallelogram. So in that case, we have vector A and vector B. We call this as a head of the vector and this part as the tail of the vector. In law of parallelogram, we can join two vectors by their tail. So tail to tail connection is made without changing the direction. So we can actually slide B and attach this at the end of A, and then complete the parallelogram by drawing two parallel lines, one to each vector, and then we find intersection of those at point P, and that point P is the tail of, it is the head of the resultant vector. So we can draw final vector going from this point of intersection to point P, and that's our resultant vector R, and it can be written as R equal to A plus B. There is another method, a triangle method, where tip to tail connection is made. So what we do here is we draw one vector and then we join the tail of the another vector with the head of the first vector. So you can see that connection here, and then whatever is the end point, we connect that end point with the tail of the first vector. So this is the resultant vector, and this is called a triangle method because it looks like a triangle, and this is parallelogram method. How do you subtract a vector? So if we need to write A minus B, how do we do that? It's very simple. We keep A as is, but for B, we just change the direction of B in the opposite direction and then find the resultant vector. So this is minus B and this is plus B. And then we apply law of parallelogram or law of the triangle method and find the resultant vector. We use Cartesian coordinate system to represent the vector. It is also called the XY or XYZ coordinate system, in which we define the x-axis as horizontal, y-axis as vertical. I is the direction for the x-axis. We call it unit vector. And J defines the direction of y-axis. It is unit vector for J, for y-axis. We have a vector F as shown in the figure. Now this vector F has both x and y components, and those components can be found if we project the vector onto the x-axis and onto the y-axis. So this vector can be written as F is equal to Fx component of the vector multiplied by direction, which is I, plus y component of the vector multiplied by direction, which is j. So this is called 2D Cartesian representation of vector. Okay, so that is being explained here. See, oftentimes because the slides uses the bold to differentiate between the vector and scalar, when I write, I use arrow to define vector, and like something without arrow is scalar. In this example, we can see that there are three different forces, F1, F2, and F3, and they all are meeting at one point. So we can call these forces concurrent forces, and they are in one planar. So they are also called coplanar concurrent forces. So for each force, we can write this as a Cartesian vector. So force F1 can be written as F1x. So we can project this on x-axis and y-axis. Now for coordinate system direction, this is called the first quadrant, which has both positive value of x and positive value of y. So it has positive I and j components. This is second quadrant, has y positive and x negative. So j is positive but I is negative. Third quadrant has negative x and negative y, and the fourth quadrant has positive x and negative y. So depending on that, we will use appropriate unit vector for each one of these force. So force F1 is in first quadrant, for F2 is in second quadrant, and F3 is in third quadrant. And this slide shows the x and y projection for each vector: f1x, f1y, f2x, f2y, f3x, and f3y. So we can write these forces as a Cartesian vector as shown in the figure. So this is first vector. The second force has Cartesian representation minus f2xi, because f2x is pointing in the negative x direction, and plus f2yj. Third has positive x and negative y, so it's positive I and negative j. And then to find the resultant force, we can combine ith components together and jth components together. So we can add only ith component parts, that is f1x minus f2x plus f3x multiplied by I, and then f1y plus f2y minus f3y multiplied by j. So this is called our resultant vector. F2R, F, we use letter R for resultant, so frxi plus fryj. Now a vector has both magnitude and direction. So for this resultant vector, we can calculate its magnitude by simply square root of x component square plus y component square. And then we can calculate the angle theta of that vector, which is absolute value of y component divided by x component. And this angle is always measured from horizontal axis, and if it is measured if it is positive, we consider that angle as counterclockwise, and if it is negative, then we measure the angle as clockwise. Okay. And now at this stage, that's the theory portion.